My name is Mercedes Valero, and I am Team Project Leader. A motivation behind this project was the fact that your phone and my phone are both covered in germs, and we wanted a way that would be safe and easy to use to prevent germs from growing and living on our phones. We started with the chitosan film, which is a well-researched, intrinsically antibacterial polysaccharide, which can be easily made into a film surface. It is currently being used by the military as a wound dressing to prevent infection and as an edible coating for food products to increase shelf stability. Silver nanoparticles were the main part of our project. They kill a wide array of bacteria, can be easily tailored for different sizes and dispersion, making them very effective for this application. The silver is oxidized with oxygen from the air to form silver oxide. This then interacts with hydrogen normally found from the aqueous environment to form silver ions, which result in cell lysis, or the degradation of the cell membrane, killing the bacteria. Now I want to go over the design goals for our film. We wanted to adhere to the back side of the iPhone, which is an aluminum oxide surface, be no more than 50 microns thick, which is comparable to protective screens or other films that are used for phones, have a spray application method that would dry overnight into a film, and have a maximum colony forming unit of 5 × 10⁵ per milliliter, which is a measure of the antibacterial efficacy of films or other antibacterial surfaces. This next part of our video will cover our experimental processes and the data that we acquired from doing them. We synthesized our nanoparticles with 2 different concentrations and a range of temperatures. We then analyzed the solution for viscosity, trying to determine if nanoparticle size had any effect, more so than the concentration of chitosan. It was discovered that the stirring up our solution actually lowered the viscosity more than anything else. Our solution was then analyzed using a stabilizer to analyze the particle size. It gives you a distribution showing the normal particle size distribution based on volume. And for 52 millimolar, this is around 47 nanometers, with the conglomerates showing there at the end. We then tried to relate this to the Gibbs-Thomson effect, correlating it with concentration and temperature, but this is a minimal data set that is not very conclusive. The solution was then poured into petri dishes and let dry it overnight to make a film, which was then analyzed for the various film thicknesses. We took various measurements, and the average film thickness came out to be around 66 microns, which is not too far from what our design goal is. The films were then peeled off from their petri dishes and cut into small squares in order to be analyzed antibacterially. We grew bacteria, E. coli, in a broth, and then placed this in an agar solution, which allows bacteria to grow and is good for cultures. This agar was then placed onto the cut-up film squares. Those cut-up films plus the agar with the bacteria was placed in a beef broth, allowing bacteria to cultivate. Then we took different dilutions of this beef broth and placed it onto agar plates, formed as a gel when cooled, which would allow it to grow as cell cultures during incubation. We did 3 separate dilutions, and we have a 0-hour and a 24-hour control, which allows us to really understand the efficacy of our antibacterial films. The comparison of the 0-hour and 24-hour cell culture counts revealed that all 3 film surfaces managed to kill bacteria, with the 26 millimolar concentration film killing 90 cell cultures and the 52 millimolar killing over 330 of these cell cultures. This translates into colony forming units ranging from 0 to 3.4 × 10⁵ colony forming units per milliliter, which is well within our design goals.